All right, we're going to look at some circles here, and specifically the arcs and angles formed within these circles. This Google Slides sheet here is what you're going to fill out and turn in at the end of the video. If you want to watch the whole video once and then go back and listen to it while you complete the task, that might help out with filling in some of the blanks here. The vocabulary we're going to use, we're going to look at central angles and inscribed angles. We're going to create central and inscribed angles using Desmos geometry, which should be new to some of y'all. And then we're going to look at chords and secants and the angles formed by the chords and secants. The next few pages are what you'll be filling out. There's some questions you have to answer. The construction you're going to do on Desmos, it gives you the step-by-step walkthrough, and then some other fill in the blanks and some questions to answer. So let's get right to it with Desmos geometry. This is just desmos.com/geometry if you've never been there. We're going to start with a circle. So I choose the circle tool. You start clicking in the center of where you want your circle, and then the next click is the outer edge of the circle. So I'm going to make it there. I can move the circle around by clicking in the center point. It moves it around, but it keeps the outer edge locked. I can move the outer edge, and it's going to keep the center locked. Or if I click on the green circle itself, I can move the whole thing. So there's my circle. I want to start with a central angle. A central angle is formed by two line segments that start on the edge and end at the center. So here I have two radii. Each one of these blue lines is a radius. That creates a central angle. The angle tool here can give me the measure of this angle. When I click on the angle tool, it tells me step by step how to make it. So choose a point, that's one leg, choose the vertex, and then choose the other leg. So this is an 83-degree central angle here. The arc created by this central angle, I'm going to call it arc. Actually, I need to label a bunch of my points. So let's label this point here A, this here B. This arc here that is orange is now arc AB. So arc AB in orange is an 83-degree arc. We measure the arc by its central angle. If I move point A, it becomes arc AB that measures 124 degrees now. So this is a central angle. Central angles have to have radii as their edges, and the center has to be, the vertex has to be the center of the circle. Next, we're going to look at inscribed angles. So let me delete that. The inscribed angle of a triangle is formed by two line segments that are on the circle itself. So rather than the vertex being on the center, the vertex has to be on the edge of the circle itself. So now I have inscribed angle A C B. I don't want to call that C. The center of the circle needs to be C. There we go. So I have inscribed angle ADB that creates this arc here. Now, this inscribed angle has a measure of 60. I want to look at the measure of this orange arc now. Actually, I want to change that away from 60. Let's get a new number. Let's go 44. The measure of this orange arc AB. Remember, the measure of an arc is measured by its central angle. So if I create the central angle back on here, from A to C and from B to C, the measure of this angle C is the measure of this orange arc. So use my angle tool, and it is 87 degrees. I can move this around, and it's going to move all those degrees there. I want to get nice even numbers so that we can see the relationship here. Inscribed angle ADB is 53 degrees. the central angle is 106 degrees, which means this orange arc length is 106 degrees. The relationship between these two measures, if you notice, the inscribed angle is exactly half of the central angle. That's always going to be that way. No matter how I move this around, unless it rounds off by a little bit, it might be off by 1 digit. So there, for example, the digits are rounded off. So ignore that. If the rounding is correct, the inscribed angle is always half of the central angle. What's kind of neat here is if I move point D around, the inscribed angle stays the same measure, 41 degrees, no matter where it goes. Kind of interesting there. We are next going to look at a different angle formed by different chords. So let me get rid of everything. Whoop, I guess everything. Let me give another circle. Let me create two. I can't use actual chords because Desmos does weird things when you move them around the way I'm about to move these around. But here are two line segments. I'm going to mark them all with points. Now I have these intersecting lines. They're supposed to be chords, but to make it work like I want to, I have to go outside the circle. So I want to look at the two angles created by these chords. This is one angle, 35 degrees. The other angle is a vertical angle, so it is all... Okay, that threw me off. I went through the wrong point. Go away. Now I want to look at that angle. It's also 35 degrees. Since they're vertical angles, I knew they were going to be the same. What I specifically want to look at here, though, is how these two angles are related to the arcs that they create. So this first arc here, this orange arc, I want to call that arc A. This red arc over here, well, it's not red yet, but it's about to be. I want to call arc B. So, intersecting chords create this angle here, 35-degree angle, and the angles pass through these points, creating these two arcs. I want to look at the relationship between this 35-degree angle and these two arcs. So, remember the way we measure these arcs is by their central angle. So, I'm going to try to not get the circle too polluted, but I want to show the angle inside there so that we can look at the arc measure. If I put those segments here, I'm going to make them gray so that they sort of blend in a little bit. And the angle of that red arc is 43 degrees. The orange arc is 28 degrees. Make these gray so that they stand out less. Okay, so now, no matter where I move these points around to, they still pass through arc A and arc B. Okay, I want to look at how this 35-degree angle is related to these two arc measures here. Orange arc is 29 degrees, red arc is 41 degrees. There is a theorem that tells me how these are related, and you may notice if you observe closely enough, 41 degrees and 29 degrees. If I add those together, I get 70 degrees. These angle measures here are exactly half of that. So this theorem, it tells us that if two chords intersect in the interior of a circle, like these do here, the angle created by the two chords, 35 degrees, is exactly half of the sum of the two arc measures. I can move that around anywhere. I can make this a bigger arc. Let's go like this. And no matter what we do with within rounding, this 47-degree angle is half of the sum of these two arcs. So that's 94 if I add together the orange and the red arc, 94, half that, and you get this angle 47. The next theorem we're going to look at, the next type of angle we're going to look at, is similar to this, except these two chords, instead of, whoa, I don't want to do that. Instead of these two chords intersecting inside the circle, I want these two chords to intersect outside the circle. So like this. Now, let me get it looking the way I want it to look. Okay. Here I have this 40-degree angle caused by, this is now a secant, not a chord. A secant is when the chord basically extends outside the circle. So I have two secants that intersect on the outside of the circle. The angle of the two intersecting secants, 40 degrees, is again related to arc A and arc B. If the intersection point is outside the circle or in the exterior like it is now, we don't add together arc A and arc B, but instead, if you can observe, 102 minus 22 is 80. So the theorem here tells me that if I half the difference of arc A and arc B, it's going to equal this angle here. So 102 minus 22 is 80, half that to get 40. I can again change this all around, and it's still going to hold true. Here's the 35-degree angle, which should equal exactly half of the difference of arc A and B. So take arc A, 94, arc B, 94, minus arc A, 24, we get 70. Exactly half that is 35. So, to recap these last two theorems, if the secants or the chords intersect outside the circle, then the angle they form is half of the difference of arc A and B. If this intersection point is inside the circle, like this, then the angles they form are exactly half of the sum of arc A and B. Hopefully that teaches you a little bit about circles and the angles that are created within them by chords and secants. Have a great day.